We're continuing with word problems that involve systems of linear equations. So if you remember, what we're doing here is that we have the luxury of having two different idle no's, which actually makes them easier. And once we have the system of linear equations set up, so we need two equations because we have two idle no's. We can use all of our tools from the previous sections to solve them. We can do substitution or elimination. So let's get started here, and we're getting to some more complicated ones. But we're going to do distance equals rate times time. Now we actually, let me see if they have that for us. Yeah, our table's down here. So we did these earlier in the textbook where we did this, and I think this is easier now because we can set up two different equations with two different idle no's. Before we had to build one idle no off the other, so I think this is a little better. So we're going to build our table here. We've got two people driving. We've got Joni and Kelly, and I've got each of their rates just dropped in like we would have done earlier. Now, we don't know how long each of them is driven, so I don't know, so I would do my dictionary here. J is Joni's time in the car, and K is Kelly's time in the car. So I've got two idle no's. Now, what we did before is the same. We're always going to create that distance column over here where we just multiplied across. You remember this? Rate times time equals distance. Okay, now our table is set, but we have to make two different equations. So let's build one. One of them is the same kind of thing we saw before. They were traveling the same distance, so we could set them equal to each other. So each of these, again, remember how this worked. This is math language. It doesn't look like a distance, but it is. And so is this. And so they traveled the same distance, so those are equal to each other. Now, it also told us that Kelly's time in the car is a half an hour less than Joni's. So look what we can create for our second equation. Kelly's time in the car is half an hour less than flips it around, than Joni's. And we now create two equations. Okay, so we have everything we need to solve this, and we are, if you look here, we're set up perfectly to do substitution. I already know what K is, so I'm going to just drop that in replace of K. We distribute and do our solving. Now we get J is 3 hours, so 3 hours in the car for Joni, and now we plug that back into our other equation, just like we've always been doing. Plug that back in and solve it, and we get 2.5 hours. Yeah, we don't need the rest of that. Okay. All right, let's try it again here. I've got two people. I've got Mitchell and I've got Clark. And so rate, we always do this backwards, remember. So it's rate times time equals distance. So I'm going to make my chart. So Mitchell's going 60 miles an hour. Clark's going 75. Now, just like before, we don't know their speeds, so I'm going to call those X and Y. So I'm going to make my dictionary. So I've got the two speeds here. I don't know Mitchell's speed, I don't know Clark's speed. Now we always finish our table, so we're going to multiply across. Okay, so this is the column we're going to build an equation out of, the distance column. And we know that the one person caught up to the other, so they traveled the same distance. So just like on the last one, we can set those equal to each other. Now, what we need is, let's see. Oh, say, Clark's time in the car is 1 hour less than Mitchell's. So Clark's time in the car, oh, you know what? I called these speed. They're not. They're Mitchell's time and Clark's time. Sorry about that. So I wasn't paying attention. So Clark's time is what we've got. 1 hour less than Mitchell's. Okay, well, less than makes us flip it around, and I get this. So now I'm turning this into something we can understand better, but Clark left 1 hour later. It means Clark's time in the car is 1 hour less than Mitchell's, which I can turn into this. And now, oh, I'm sorry, I'm messing everything up here. Let me do this again. Sorry, everyone. So we're using Y is X minus 1. Okay, so let me fix this real quick. So we don't know the times, so I don't know x and y, and they were the times, not the speeds. Now we build that second equation. Clark's time, which is y, is 1 hour less than Mitchell's, creates my second. Okay, so I'm ready. I'm already set up for substitution. This is what y is. It's x minus 1, so I'm going to drop that in. Now I'm distributing. Okay, now the rooms are clean, but x is the I don't know is in both places, so we'll never get them alone. Now I don't want to leave this room totally empty, so I'm going to take away 75x from this side. Okay, divide both sides by negative 15. So if we got weird signs here, but it'll take care of itself when we divide a negative by a negative. And 5, right? 75 divided by 15 is 5. Yep. Okay, so we get x is 5. Now that is 5 hours in the car. X was Mitchell's, but let's put it back into either equation you want. But I'm going to put it in here. Y is 5 minus 1. So y must be 4. So 5 is Mitchell's speed, or time in the car. I keep doing that, I'm sorry. 5 is Mitchell's time in the car, and 4 is Clark's time in the car. Okay, I'd really recommend you pause this. Okay, so Charlie and Sally. So we've got Charlie's time in the car. We're going to call it x. We've got Sally's time, and we're going to call that y. Now we're going to need two equations, but we're going to start with our rate times time equals distance. Okay, so Charlie is going 36 miles an hour, Sally's going 42. Now I don't know their times, and so we made our I don't knows in our dictionary over here, so I got x and y. Now we multiply across 36x, 42y. Okay, so they caught up to each other again. Doesn't always have to be this, but it turns out this one is another. So they're equal to each other. The distance in math language is the same. Okay. So Sally left 15 minutes later. So Sally's time in the car, which is y. Sally's time in the car is 15 minutes less than Charlie's. And less than makes us flip it around. Now, we saw this in the earlier section, if you remember this. I have to make sure, I'm in miles per hour, so I have to make sure that I'm matching up. So this is 0.25 of a mile, or so hours. I've got a quarter of an hour. So if you weren't sure, remember how I did that earlier? 15 divided by 60, that's going to get you 0.25. Okay, so I'm perfectly set up for substitution, so I'm going to drop this in. Now we're going to distribute. Okay, I get 10.5. Okay, now let's go ahead and solve. Well, we have I don't knows in both rooms. The rooms are clean, but I have I don't knows in both rooms. So let's get them back together. And we get negative 6x equals negative 10.5. I'm going to divide both sides by negative 6. And I get 1.75. That is Charlie's time, so that's hours. That's Charlie's time in the car. Now, we can go back to either equation, but this one is set up perfectly to do this. So I'm going to go back where Sally's time in the car is 1.75 minus 0.25, and I get 1.5. So Sally's time in the car is 1.5 hours. Now, to make this more clear, maybe I should put it up here, 1.5 and 1.75. Okay, now we're going to get to a different type of problem. I think at first this is going to seem a little overwhelming, but after you do a few of these, this is actually pretty easy. So the idea is this: if you have a plane or a boat or whatever, in and of itself, the boat in this case can go a certain speed, right? It's manufactured to have a top speed. Well, if you're fighting the water, so there are two possibilities. The water might be helping you, in which case you'd be going faster. So the current might, if you're going the same direction as the current, it speeds you up. Or perhaps you're going against the current and it's slowing you down, so it's fighting you. So that's what we're looking at here. So let's build this. I hope you had enough time to see it, but I'll talk you through here. So what are idle nodes? Here's our dictionary. We've got the boat in still water. Like, this is just what the boat is made to do. But then there's the current of the water. Okay, so if we're going downstream, the boat has a speed and it's getting helped by the rate of the water. Do you see it's helping it, making it go faster? Now, if you're fighting the water going upstream, it does the opposite. You have to fight the current of the water. Now, we didn't spend a lot of time on the previous screen, but it's telling us they went downstream for 4, they went upstream for 5, and they both went 60 meters or whatever. I didn't really look. Okay, so now let's set up two equations. So we can do the two, we're just multiplying across, and this is where we're going to get our two equations. Distance, or rate times time, I'm just doing that. We've been doing that all along. But this time we know the actual distance is 60. We can do this again. We know the actual distance is 60. Okay, now we have two equations, so they've got it here. Now here's the trick to these. We'd like to do the elimination method, but before you just distribute the 4 all the way through here and the 5 all the way through here to tidy these up, these are much easier. Because the entire left side is being multiplied by 4, we can just divide it by 4. Let's see if they did that. No, they didn't. So if the entire left is being multiplied by 4, let's divide it. But if we do it to one side, we got to do it to the other. But look what it will leave. It'll leave s plus c equals 15. Now let's do the same trick here. If we divide this by 5 on one side, we got to do it to the other. We get s minus c is 12. Now, what's so great about that? Well, look at it. It's perfectly set up already for elimination. And this works, as far as I can remember, on every one of these. So much easier than distributing and trying to do all that work. So let's just turn this into a big addition problem. The c's will already cancel, and I get 2s equals 27. We'll divide both sides by 2. And 13.5. Okay. Now I don't remember our dictionary. What are we looking for here? So that was s. So that was the speed of the boat in still water. But now they also want the speed of the current. So I'm going to use either equation that I want. I'm going to choose the second, but it doesn't matter. And you can also use any version of the equation that you want. So I'm not going to start with these harder ones. I'm going to go down here and use these simpler versions because it'll still hold true. So 13.5 minus c equals 12. So this is weird. I don't know if we've seen this. This is like a -1 in front of the c. I can't lose that sign. He's got to stay there. Now I'm going to subtract from both sides. Now, negative c equals -1.5. We could think of it like the opposite. Well, so c obviously has to be 1.5. The other way you could think of this is you're actually dividing both by a -1. Either way, you get the same. C is 1.5 miles per hour. So we have the two speeds. Okay, I'd recommend you try are there two of these? Yeah, well, we've got another one, but so we've got upstream and we have down. And we're going to call, I just always use x is going to be the speed in still. Y is going to be the speed of the current. All right, so we've got rate, time, and we have our distance. So, okay, so upstream, that makes me, my brain hurt a little bit, but upstream you're fighting it. So it would be minus because you're going up against the current. Downstream you're going with it, so you'd be going faster. So it took 12 hours to go upstream. It tend to come down because they were going faster. And did they go the same? Yeah, they went up and then they came right back. So they both equal 120. Okay, well now we have everything we need to create two equations. Now where are they? Well, we are always doing rate times time. We know the distance is time, but here's what we can do. This is still a distance. Well, that must equal this. They have to be the same thing. So rate times time has to equal 120. So I'm going to do that. And then I'll do this one. That's rate times time, and that has to be 120. Now I'm going to do the trick where we're immediately going to divide both sides by 12. And so I'm going to have x minus y equals 10. I'm going to divide both sides here by 10. And I get 12. Now remember, the beauty of this is it's already set up for elimination. We can just go down and get 2x equals 22. Divide both sides by 2. And x is 11. So 11 is the speed of whatever we're talking about, the boat, okay? So 11 miles per hour. Now we can use any equation we want to find the speed of the current. And so I'm going to just use this top one, and I get 11 minus y equals 10. So negative y is negative 1. So I just subtracted 11 from both sides. So the opposite of y is the way you could think of it, or you can just divide both sides by negative 1. So the current is going 1 mile per hour, and the boat is going 11. Okay, try another one here. Again, I really recommend you try this. So I'm going to set up my dictionary. Okay. So speed of the current, whatever. Okay, so we're going upstream again, and we're going down. Rate times time equals your distance. So upstream, he's fighting. Downstream, it's helping. 4 hours to go up because it's harder. 3 hours to come back. Oops, I was jumping ahead here. So we know the number for this kind of problem. So those are both 24. Okay, set up my equations. I'd have 4. So this is distance, or the rate times the time. That's the rate times the time. And we know now it equals an actual number. I get my second equation by doing the other one. Okay, I'm going to do my trick. I'm going to divide both sides by the 4 right off the bat, and I'm going to get x minus y, 6. This one I'm going to divide both by 3. I get x plus y equals 8. Now, set up for elimination. So the y's are immediately gone, and I've got 2x equals 14. Dividing both sides by 2, x must be 7. Okay, so if x is 7, let's go back here. I'm going to use this equation. You can use any one you want. And I've got 7 minus y equals 6. So minus y must be negative 1. So I'm just subtracting 7 from both of those. So then y must be 1. So the canoe in still water is 7 miles per hour. The current is 1 mile per hour. Okay, is there anything different about this? Not much. So the only thing that I can see that's different here is that he doesn't travel the same distance both times. Yeah, this isn't much different. So same thing. Speed of the jet with the wind, speed of the jet fighting the wind. This time, each time they spent 3 hours going, and they just have different distances because they didn't go as far. So everything works the same. Now, I'm not going to, it's the same. I would divide both sides by 3, and I don't think they're going to do that. Yeah, they distributed, but you're going to get the same thing in the end. So we're going to get J as 347. You plug it back in, you'd get your W. So 347 is the speed of the plane. The wind is 18 miles per hour. So let's do one here. Let me check real quick. Yeah, this is our last type of problem. Okay, so we've got x is the plane speed. Y is going to be the wind speed. So I've got headwind and tailwind. and then rate times time equals the distance. Okay, so headwind, you're fighting. Tailwind, it's helping you. So 5 hours in the tail, they both 5 each time. Okay, so which one? Tail, when they have the tailwind, they get 1,325. When they have the headwind, yeah, they can only go that. Okay, so everything else is the same. We're just going to do 5 times x minus y equals 1035. Just doing rate times time is another way to say 1035. And we're doing it again. Okay, I'm going to divide both of these by 5 right off the bat. I'm going to do it here too. So I'm going to get x minus y equals 207. And x plus y is going to be 265. Okay, so same thing we've been doing. Everything works the same from here. Elimination, the y's are gone. We've got 2x equals 472. Divide both sides by 2. So x is 236. Now that's the speeds plane, so 236 miles per hour. We can use any equation to find the wind speed. So I'm going to use this one again. So I think I keep using the harder one. Oops, that's a 6. Minus y equals 207. Okay, so negative y equals negative 29. So y must be 29 miles per hour. That's the speed of the wind. Okay, one more of these. Again, pause the video if you want to try this, but it's the same. So x is the plane speed. Y is going to be the wind speed. So I got headwind, and I've got tailwind. Rate times time equals distance. Okay, so a headwind is going to hurt you. Tailwind's going to help you. 4 hours and 1728 with the tailwind. 4 hours and 1536 with the headwind. Okay, everything's going to be the same. We're just going to set up our two equations. I'm going to divide both sides by 4. So I'm going to get x minus y equals that gets me 384. I'm going to get x plus y equals 432. Do my big addition problem, and I get 2x equals 432 plus 384. Get 816. Divide both sides by 2. And x is going to be 408 miles per hour. Okay, so I should stop using the harder one. So this is 408 miles per hour. Let's use the easier one. So 408, I'm using this bottom equation, plus y must equal 432. So I'm solving for y, subtracting 408 from both. Get 24. So the wind speed is 24 miles per hour. Okay, so we've seen this distance equals rate times time earlier in the book, and I think it's actually easier if you have two different idle no's. So then you set up your two equations, one for each idle node, and then use your either substitution approach or elimination approach to find one of them, and then plug back in to find the second.